Hello folks, we're back here and now we are going to start with chapter 17. Chapter 16 was electric charge, electric force and electric field. Coulomb's law, right? Plus Gauss's law. Here you go. What we're going to do now is something else called electric potential energy. We have seen an analogous idea, an analogous concept in physics 120. It is called the potential, at the time it was called the potential energy. But now I'm going to be very specific what type of potential energy was there. The potential energy that we saw in physics 120 was the gravitational potential energy. It was the potential energy due to a very large mass. Okay? And what we're going to do here, we are going to talk about the electrical counterpart of the gravitational potential energy. It's, like I said, in the case of the there is the electric potential energy and there is the electric potential. Okay, so let's make it very clear. Electric potential, the masses can be whatever size, the relative masses can be whatever size you want. Okay? But the electric potential, in the electric potential, the electric charges can be whatever size they are. Okay, let's put it this way. Similarly, in the gravitational potential energy, the masses can be whatever size you want. Okay? And both the electric potential energy and the gravitational potential energy is the energy of the system that you are considering. You know, it's going to be, at least in the case of the gravitational potential energy, it's going to be, the system is going to be at least two masses. In the case of electric potential energy, the system is going to be at least two charges. You cannot have a potential energy due to just one mass of just one charge. It has to be at least two objects. Okay, that's a very interesting thing. Okay, think about that. Let's write that down here. Let's document everything that we're talking about. This is 27, 21. Electric potential energy. Let's go the summary so far, right? Electric charges. I like to do this type of documentation. Here you go. We have electric charges, then we have electric forces. That's what I call the summary. And then we have electric field. What comes next is called electric potential energy. So what is the analogous for physics 120, right? Let's do that together. Here you go. I'm going to put it side by side, how what we study in physics 120 or mechanics relates to what we're studying right now in physics 122. Okay, here you go, physics 120 and physics 122. So you can get your mind better organized. Here you go. In physics 120, I introduced you to the concept of mass, right? In physics 122, we have this other idea, which is the electric charge. In physics 120, that is what we call the gravitational force, gravitational attraction, you know, the law of universal gravitation. In the case of the electric charge, we have the electric force, which is going to be the Coulomb's law. Coulomb's law. In physics 120, we have the acceleration of gravity, which, by the way, is just another name for the gravitational field. Acceleration of gravity. Just another name for the gravitational field. That's the analogy between 120 and 122. What we have here, we have an electric field. Okay. The gravitational force must be between at least two masses. The electric force must be at least between two electric charges. But when it comes to the acceleration of gravity or the gravitational field, we are talking about the gravitational field of, you don't have to have two masses. It can be the gravitational field of at least one mass. We can talk about that, the gravitational field of only one mass, but not here. Here we cannot talk about the gravitational force of one mass. We always talk about gravitational force of two masses. Same thing here. The electric force is always the electric force of at least two charges, right? At least two sources. We can put this in this way. Here you go. Can put, and we can come up with even, here's the source, right? Source of gravitational field, source, and the source of gravitational field, and the source of an electric field. And I'm gonna keep this one empty here. At least one source, right? In order for a force to exist, a gravitational or electric force to exist, you must have at least two sources, two masses, or two masses or two charges, like that. What about here? For the electric field, you may have only one source. Make sense? For the field itself, you may have only one source. Yeah. And that's exactly what the acceleration of gravity here on Earth is all about. The source of the acceleration of gravity is the Earth itself, is the mass of the Earth. Then what did we study next? We study the potential energy, which in reality is the gravitational potential energy. The gravitational potential energy, that's what it's all about. And here what we have is going to be the electric potential energy. I'm going to abbreviate by PE. In this case, must have at least two sources, just like before. In order to have a gravitational potential energy, it is a system of at least two sources, two masses or two electric charges. That's how the potential energy exists. The gravitational potential energy and the electric potential energy. And what we're going to see next, we didn't study in Physics 120. What we're going to see next is not the electric potential energy, it is the electric potential. But we could have defined a gravitational potential if you wanted. We could have that. We could have done that. In this case, you may have only one source, just like for the electric field. But there is an important, see, there is a very important parallel between the electric field and the electric potential. Okay? It may be produced by only one single source, yeah? The field and the potential, it may be produced by a single source. Whereas the force and the potential energy, you must have at least two sources. At least two sources. What else? Which other differences do you have here? It's important to do that just to organize your mind, okay? What else do we have? In order to understand what something is, you have to understand the difference between them. In the case of the gravitational force, it is a vector. In the case of the field, it's also a vector, whether it's the gravitational field or the electric field. However, in the case of the potential energy, as you saw before, the potential energy is not a vector, it's a scalar. Similarly, the gravitational potential and the electric potential are scalars, scalar quantities. So look very carefully at that so you can have a better understanding of how this whole thing is put together, right? This whole theory is put together. Here you go. Like that. And it goes exactly in this order. One depends on the other. Without an electric field, without an electric force, we cannot define an electric field. Without the concept of electric field, we cannot define the concept of electric potential energy. Okay? Now let's illustrate. Let's see how we can illustrate that. And your book has a very interesting illustration. I like that illustration of the book. Okay? But I think the illustration of the book is a little bit premature. It's not generic enough. But he's doing that for one very important reason. See what's happening? He's putting a very large object next to a very small object. Okay? That's what he's doing. It doesn't have to be, this one doesn't have to be a small object. It can be a large object too, but that's okay. So the gravitational potential energy has, for the gravitational potential energy, like I mentioned, you have to have two objects. That's how it is defined, and it's a very good definition. Okay? So let me illustrate here in another way. Here you go. If we have the Earth right in here, and we have a small apple, it's not falling, it's right now is on the surface of the Earth. And I can even dramatize what's happening here. Here you go. I have my cell phone right in here. Okay? If I raise my cell phone against the force of gravity, I'm going to add potential energy to my cell phone. Okay? Here you go. I'm going to get this guy here. Move from one place to another. I am adding potential energy. Like that. You go. I'm gonna put it side here on the side. Adding potential energy. I like to say I'm pumping potential energy. Adding or pumping slash pumping potential energy. Okay. Okay, now that's the left side. I'm gonna even put a symbol for the mass. In this case, here you go. Mass, M, little m. And I'm going to put a big M here. Like that. Like that. Here you go. But now on the right side, we have something different. Instead of masses, what you're going to have? What you're going to have? You're going to have electric charges. I'm going to erase this guy because I don't need it anymore. So you can have a nicer figure right here. So instead of having a big mass here, we're going to have a big charge. Instead of having a small mass here, I'm going to have, and by the way, let's say I'm going to have a charge. A small charge can be a large charge too, but I'm doing that just to prepare you for what is going to come next. I'll call this one a positive charge, and this one here is going to be a negative charge. Why is that? Because I want to keep the analogy between the forces of attraction between this big mass and this small mass. I want to show to you that this big charge is also attracting the small charge. So here we go. Is moving upwards. In both cases here, we are adding potential energy. We are pumping potential energy into the system. The potential energy that is being added is not just the potential energy. We are not adding potential energy just to the small mass. In reality, we are adding potential energy to the small mass and the big mass. That's what we're doing. Okay? But instead we tell the student that we're pumping potential energy into this little mass. That's not true. Okay? It's easier to understand this way, but in reality, strictly speaking, we are adding potential energy to the two masses. Here too, we are adding potential energy to the two charges. And here is gravitational potential energy. Here is electrical potential energy. So let's put that here. Here you go. Let's put the gravitational potential energy first, because that was the first one that we saw. Gravitational potential energy, electric potential energy. That's the type of illustration that you have to have in mind. Okay. We can do that for here, this charge is, and I can even put a force of attraction here, right? If I'm applying a force to this mass, the mass, stay at this height. If I release the force, the mass is gonna fall back. it's gonna lose potential energy. That's the direction of motion. Okay, so I can do the other graph that is in your book. Your book has a similar graph. Now we are not gonna add potential energy, we are subtract potential energy. Subtracting potential energy. Pumping out potential energy. How does it work? Okay, first start here at the top and move to the bottom. Same thing happens right in here. Okay. But the concept is the same. It's going towards the larger charge because they are attracting each other. I'm going to do something else too. Here you go. I'm going to make those two dashed. So you know it was there initially. Here you go. And if you go to the top, here you go. Here you go. Started here, ended there. We can do the same type of game for charges of same signs, but we do not have these analogous for the mass because the force is always attractive, right? So let's do that. Here you go. I'm going to do now, gravitational electric potential energy for charges of same sign. For charges of same sign. We do not have this for masses. So I'm going to do the following. Q greater than 0 and lower Q greater than 0. Okay. Okay, so those charges, they tend to repel one another. So when I approach the two charges, the tendency is to resist the motion to get to approach to have the one approaching the other. So we are not subtracting, we are adding potential energy. Exactly the inverse, right? It has it's like compressing a spring. You compress a spring and you are adding potential energy. So we can come up with this mechanical analogous. Electric potential energy charge of same sign. Mechanical analogous. Mechanical analogous. Compressing a spring. Like that. Like that. Whether both charges are positive, whether the both charges are negative. You can picture that, right? And then we can do the other way. We can subtract potential energy. And everything is going to be inverted here, right? So this guy is going to start there at the bottom and it's going to end up at the top. Here you go. The arrow is going to move upwards. I don't have to move the charge. The charge goes on its own naturally. Subtracting. Yeah, let's not adding reducing, right? It's better put the reducing potential energy. Okay. So here you go. I'll copy that and paste there. Here you go. Right in here. Increasing, even better. Let's put increasing potential energy. Decreasing potential energy instead of reducing. That's the qualitative idea of potential energy. Analogous to compressing a spring. Here the spring bouncing back. In this case, the spring bouncing back. One end of the spring, the other end of the spring, right? Let's see. Analogous to a compressed spring. Here to a compressed spring. Spring bouncing back. So bouncing back. Bouncing back. Analogous to compressing a spring. Those are the qualitative ideas of potential energy, whether it is gravitational potential energy or electric potential energy. Here I made the analogy with a mass. Okay? Here the analogy is that for a spring, but I didn't illustrate it. It's not illustrated. Okay? The book did something similar, right? But I went further than that. Here you go. We have this meteor losing potential energy, going to lower altitude, gravitational potential energy. We have this positive electric charge losing potential energy because it's approaching the larger electric charge. Okay? That's what this is all about. It's just a qualitative illustration. And if you recall the definition of potential energy, what is the definition of potential energy? Is the change in potential energy is minus the work done by the field force. We usually call that the conservative force. Okay, the book called that a field force. It's minus. You have a minus sign. So the change in potential energy is defined in terms of the work done by a special type of force, classified as a conservative force. Okay, here you go. Insert equation. Here you go. You gotta do the delta. Delta U is gonna be, minus the work done by the conservative force. We denote the conservative force by this little c. Remember I told you that there are very few conservative forces there, right? The book called that the field force. The book used a different notation. We call it the field force. I call it conservative force. Let's write it down here. We'll call the field force. Okay. So potential energy is energy stored in the field. What does it mean? And the field is that field that exists between those two sources. Whether the sources are two masses, whether the sources are two electric charges. So we say let's start now. The electric potential energy is energy stored in the electric field, or in our system too. We can put it this way as well. Okay, and here you go. He has the similarities, which I did that for you as well. So here you go. You're going to remember that the gravitational potential energy is given by this relationship between the two masses. Right? So here you go. We can put that in my notes here. Gravitational potential energy between two masses. We didn't prove that in physics 120 because it involves calculus, okay? So you're only, all you have to do is to memorize. So here you go. I'm going to put that here. I'm going to put according to the notation of the book. Here you go. He put sub G, right? To remind you that it's a gravitational potential energy. And what's that? We got a big G, we got a M, we got a M, and we have to divide by the distance between them. Here we go. Source 1, source 2. That's going to be the potential energy between two masses. Here you go. And we have a negative sign there. What about the gravitational potential energy between two charges? Between two charges. No, not the gravitational potential energy, the electric potential energy between two charges. Okay, we're going to put sub E here. Instead of G, we are going to have a K. Instead of a negative sign, we are not going to have a negative sign. Instead of M, we are going to have charge Q. Instead of M2, you're going to have charge 2. So if you remember this one, you're going to remember this one. We do not need the negative here. Why is that we do not need the negative? We do not need the negative because if those two charges are attracting one another, one of the charges automatically will have a negative charge, a negative value. Okay? So in the case of attractive charges, for they're attracting one another, the negative is already placed in either charge 1 or 2. Okay? In the case of charges that are attracting one another, just like the case of the masses, just like in the case of two masses, okay, the negative sign is already placed in one of the charges, either Q1 or Q2. So that is the qualitative idea of potential energy, electric potential energy and gravitational potential energy. And we can solve problems using either the concept of force or the concept of energy. The concept of energy is more convenient because it is a scalar. It's easier to work with a scalar than to work with forces, which are vectors, right? So we can write that down here. We came up with the idea of energy because it is a scalar concept. Being a scalar, it is much easier to work with it mathematically. Okay? Let me put in another way. The same problems that are solved with the concept or idea of force can also be solved using the idea of energy. Although, in many cases, it is easier to solve a problem using energy. Okay? Now let's do an example here that is in the book, example 17.1. Right? Let's study this example, what it's all about. In a thunderstorm, charge is separated through a complicated mechanism that is ultimately powered by the sun. Okay, in a thunderstorm, you have lots of electric charges in there. Okay, a simplified model of the charge in a thundercloud represents the positive charge accumulated at the top. Okay, that's a simplified model. Okay, and a negative charge at the bottom of the cloud, a pair of point charges. Okay, what's the electric potential energy of the pair of point charges? Assuming that U equal to 0 whenever the two charges are infinitely apart. Okay? So what we have here, whenever you have a thundercloud like this one, basically we have differences in electric charge. Positive charges at the top of the cloud, negative charges at the bottom of the cloud. That's a simplified model, a very good simplified model. And this thundercloud has some potential energy, has some potential electrical energy. Okay, I once was talking to this pilot, right? He understood meteorology. And he was looking at the clouds there in the distance, and he was talking about the potential energy of the clouds. Yeah, the clouds has electric potential energy. And that potential energy can be used to make something good or make something bad, right? You can get floodings. This potential energy can be used to flood places and destroy places, or this potential energy can be used to grow plants, right? To water the plants, and so on. So let's take a look. What's the electric potential energy of the pair of point charges? That's easy, right? You already know what the equation is. I'm gonna do that for you anyway. Here you go. That's a simple type of problem that's easy to solve. I'm going to get my favorite software here. Here you go. The one I like to use. Electric field. Now we're going to talk about electric potential energy. Electric potential energy. What's going on here? Electric potential energy. Okay, U is going to be given by K Q1 Q1 times Q2 divided by the distance between the charges. Here you go. K shouldn't be difficult to remember, right? K is what? K is 9 times 10 to the 9, right? And then we have the units of K. In this case, the unit of K is going to be newtons. Meter is square. Do you remember that? Per coulomb is square. Hopefully I got the units correctly. Okay. Which, by the way, is also equal to joules times meter divided by coulomb square. That's another way of writing that down to here. This guy here too is also equal to joules times meter divided by coulomb square. Another way of writing down the same units for K. Q1 and Q2, here you go. Q1 is equal to 20 coulomb. Q2 is equal to minus 20 coulomb. Let's substitute those values. I'm gonna put K here. I'm gonna do one by one. I'm gonna do it in the long way. Q2 there, and Q1 there, and Q2 here. Note that the potential energy is negative. Okay. Oh, we gotta put the distance too, right? What's the distance? 8 kilometers. Let's write down here. 8 kilometers is 8,000 meters. You gotta put that in all SI units. Here you go. R goes right in here. And here you go. Newton meter is joules. Newton meter is joule. That's the type of potential energy that we have. Note that the negative, we have a negative sign here. Potential energy is negative. What does it mean? That the charges are attracting one another, that the charges are bound to one another. That's what negative potential energy means. The charges are attracting one another. Here you go. Negative potential energy means that the charges are, in this case, attracting each other. In this case. So let's see, it put minus 1 times 10 to the 9. Let's see if it matches what I got. Oh yeah, I didn't put the value here. Yeah, but it's 10 to the 9. Minus 1. Why minus 1? Oh, it's 50. Oh, it's 50 coulombs and plus 50 coulombs and minus 20. Okay, plus 50 coulombs. Okay, here you go. Now we got it. Calculate. Here you go. 1.1. He put 1. He rounded that down to minus 1. Okay. 2-point charges like sign. Okay, let's do this. When you do is 2-point charges with like sign, it's gonna be positive potential energy. Here you go. 15 meters electric potential energy. If you do the math, you're gonna get 0.018. Let's see, what's the other, let's close that, right? Charge Q is free to move. No other forces act on it. The smaller charge, lowercase q, is free to move. Dq is fixed. Poles are initially at rest. That Q moves towards or away from big Q. Okay, it moves towards. Provided, of course, you don't shove it towards the other. How does the motion of Q affect the electric potential energy? Okay, as the little q moves away, the electric potential energy is going to decrease. So the charge is just moving naturally. Natural motion decreases the potential energy of the system. Just like my checkbook here, right? Natural motion decreases the potential energy of the system. There you go. Because those two charges are repelling one another, as they move away, they decrease the electric potential energy of the system. How do we do that for several point charges? Okay, you just sum them mathematically. Okay, let me do the, you just take it one by one in pairs. I'm going to illustrate that here for you. Electric potential energy. Electric potential energy of multiple charges. Multiple charges. I'm gonna get this one. Here you go. Let's start with 3 charges. Okay, 3 charges. Here you go. Yeah, just get this one here. And doesn't matter. Okay, here you go. I'm going to get this one as being Q1. I'll keep it capital Q. The other one is going to be Q2. And the other one is going to be Q3. Q3, right? Here you go. And let's say they're separated by known distances. Okay, here you go. D from 1 to 2, 3. Here you go. I call this one D1, 3. You have to know those distances in order to solve this problem. That's going to come D from 1 to 3. That's the notation I'm going to use. This one is going to be D from 2 to 3. And the other one is going to be D from 1 to 2. Like that. Here you go. Two to 3. Here you go. One to 2, right in there. So how do we get the potential? The potential energy is taking in terms of pairs, okay? It's the potential energy of between 1 and 2, the potential energy between 1 and 3, and the potential energy between 2 and 3. That's how we illustrate that. So we have here potential energy between 1 and 2, U between 1 and 2. Potential energy between 2 and 3. I call it U2, 3. And we have the potential energy between 1 and 3. Like that. And we sum all of them. Depending on the signs of the charge, those you may be either positive or negative. So here you go. That's straightforward like that. Potential energy between more than, potential energy among, right? 3 or more charges. Here you go. Let's put 3 charges, right? Then we do for more charges. What's it going to be? The electric potential energy is going to be U between 1 and 2 plus U between all possible combinations of potential energy and between 2 and 3, like that. And then we can go ahead. Okay, Q, the distance is D12. So we replace the R by D12. Next one, the charges are 1, 3. We replace this one by D13. And finally we have 2, 3. Alright, replaced by 2, 3. Potential energy among any charges and charges. Right, it's going to be what? It's going to be like that. Here you go. It's going to be, I'm going to put a summation sign here. See? Oh, that'll be a better summation sign. Here you go. This one that I want. Start from 2 to n, right? Goes from 2 to n, and the index here is going to be I, letter I. The charge is going to be, the charge is going to stay constant, is going to be I. Here you go. And then the K is going to be a constant. Let's put that here. Next. Then we gotta do for Q2 and the other possible combinations. But then we have to start at I equal to 3. Okay, just like what happened here. See that? You start with Q1. Q1, is combined with 2 and 3. Then you start with Q2, and Q2 is combined with the remaining charge, that's 3. You had only 3 possible terms, summation terms, but this one is going to have more because we have n electric charges. And here is going to be not D1, right? But it's going to be D2. Okay? Next, we'll keep on doing that. Next term is going to be Q3, right? But then you're going to start at I equal to 4. Ba, ba, ba. I can go ahead and write it down. Ba, ba, ba. Right? And then we can go to a point where we are going to have a J charge. Here you go. Okay, and then we are going to start at J plus 1. The J charge is downstairs. Okay, and finally, last one is going to be n minus 1. And here is going to be n minus 1, n minus 1, right? Here is going to be n minus 1. Well, it's going to be just one term, so I don't need the summation. I just replace the I with n. Just replace the I with n. We don't even need a summation in this case. Oh, I forget. Yeah, the k is already there. Okay. See, there is only one term, right? I don't even need the summation. But let's put the I there anyway. Let's put the I there anyway. So that's the genetic formula for the potential energy of a system consisting of n charges. Potential energy of a system consisting of 3 charges. Don't forget we have a k here. I can simplify. Let's simplify that. Here you go. I can get this Q1 out. I can get this Q2 out. I can get this Q3 out. I can get the QJ out. And I can get the QN out. We don't even need the QI there because it's just one term, but let's keep it anyway. And then you can practice that for 4 charges, 5 charges, see if this relation is correct or not, okay? So here you go, potential to several point charges. That's what we have. I did that for you. Electric potential energy due to 3-point charges. Okay? We did that. We didn't do it numerically, but you can do that numerically. And we are done with this section. Let's take a look here. That's going to be section 17.1. The next one is the electric potential. We got to introduce the electric potential energy before we talk about electric potential. Okay, and that's what we are going to do next. Before we go into that, let me show you what we are going to do in this chapter. For chapter 17, we will cover the following sessions. 17.1, 17.2. What else? Let's see. Electric potential, yeah. Relationships between electric field and potential, yeah. We're going to do that. Conservation of energy for moving charges, yeah. Capacitors. Remember we did the lab for capacitors. Now it's coming into dielectrics. Yeah, we can do that. Energy stored in a capacitor. Everything. We're going to do everything. From 7 through 7. 17.1 through 17.7. So let's take a little break now, and I will be back. Now let's talk about the electric potential. Okay, let's talk about the electric potential. Let's go back to my table that I have right in here. Okay, so notice that the gravitational force, I'm going to put it same colors here. Here you go. Compare those two right in here. gravitational force and gravitational potential energy. In both cases, you must have at least two sources. Do you see that? Whereas for the acceleration of gravity and gravitational potential energy, you may have only one source. So what we have here? We have here the following. If the gravitational potential energy is the scalar counterpart of the force, then it means that if the potential energy here, not gravitational potential energy, but if the potential energy is the scalar counterpart of a force, okay, then it also means that the potential, whether electric or gravitational, is the scalar counterpart of the field. The field can be either the gravitational field, which is the acceleration of gravity, or it can be the electric field. That's how you should look at that. Okay? So remember that the electric field is just the ability, right? That a given main charge have to exert a force in space if there were another electric charge there. That's what the electric field is the capability, the ability. So you have something like that for the scalar potential. For the scalar potential is derived from the electric field. So we have the following. Let's go back here. Recall the following. I'm going to write down the electric force. I'm going to use this one here, right? And I'm going to do this one also. Here you go. That's the electric force here. Force, I'm not going to put it in vectorial format. For a point charge, Q1, Q2 over R squared. The potential energy has the same numerator but a different denominator. Instead of R squared, it's going to be R. Can you remember that? So what can you say? What we can say about the electric potential? Okay, for the electric potential, what we end up having is what? Is the electric potential. I'm going to put it this way. The electric potential of charge 1, the electric field of charge 1, okay, is what? The electric force divided by charge 2. Like that. Here you go. So what do we have for the potential, for the electric potential, not electric potential energy? We will abbreviate that by the letter V. Okay, for it. What we are going to have is that the electric potential can be written in terms of the electric potential energy. Okay, and is going to be U sub E. But I'm going to do even better. I'm not going to represent by Q1 and Q2. I'm going to represent it by a big charge Q and a small charge Q, lower Q. And there's a reason for that. Okay? This Q here is much bigger than Q. Right? We do that just like the illustration that I did, that your book did as well. Okay, and now we can why do we do that? Because the definition for the electric field and the electric potential involves a big charge that's producing either an electric field around it or an electric potential around it. And this small charge must always be positive. Okay, so we're gonna write down like that. You know, big Q, by the way, magnitude, we're gonna do like that. Magnitude of big Q is much larger than smaller q, whereas smaller q is always greater than 0. We define the electric field and the electric potential with a positive, in terms of a positive electric charge. And this must be very small. Why do we do that? We do that for a very good reason. Okay, why this condition? Why this condition? You know, we do that for a very good reason. The small q must be much smaller than big Q, than the magnitude of big Q, because it cannot disturb, it cannot generate a disturbance it cannot affect, it's better like this way, it cannot affect the effect of the field and potential of the larger charge. Okay, it's just like having the Earth, which is a big mass, and an apple that was a much smaller mass. Okay, small q also, small q must be positive because we must define, you know, why is that is positive? It's not like it must be positive. We adopted q to be positive. You know, that arbitrarily we have to decide whether small q has to be positive or negative, right? So if it is negative, the field would be in a different way, right? So we adopted arbitrarily, we adopted small q to be arbitrarily positive. Positive. That's how. There's no reason for that. We just decided, you know. But this one, there is a very good reason. Much smaller. Why it's much smaller? So it doesn't affect the field of the big Q charge. So that what you have to remember, 4-point charges. Here you go, 4-point charges. The electric potential becomes, not for a point charge, the electric potential becomes what? Just get this definition right in here. And something like that. The electric potential from the big charge is going to be something like that. The unit for V is what? Okay, I'm going to write it down here. The unit for V is going to be what? It's going to be joules per coulomb. Okay, so it's a measurement of energy per unit of charge. This unit shows up so frequently that we give it a name. We call it the volts, and abbreviate also is the same letter V. Okay. So it's a measure of energy. That's what the voltage is all about. But it's a measure of energy per unit of charge. We do not have that in mechanics. Like we did with that. It's not that we do not have that in mechanics. We didn't teach that in mechanics. But if we want, we can define something like that for mechanics too. Joules per kilogram. The gravitational potential. We have the gravitational potential energy and the gravitational, we could also have the gravitational potential. Okay? So that's where the electric potential comes from. You know, every time that you have an electric charge or a separation of electric charges, we're going to have an electric potential energy, an electric potential that can be used to do some sort of work. And having an electric potential here, also means that we have some stored potential energy. That's what batteries are all about. That's what batteries are all about. Batteries are a separation of electric charge that has a potential energy. Here you go. Here's my battery. Right? You have a separation of electric charge here, positive and negative, which produces energy here that can be used for some useful purpose, for some sort of task. That's what batteries are all about. It's a storage of electric potential energy. That's what we have right in here. Okay, here you go, definition of electric potential. That's the unit of volts, joules per coulomb. That's another way of expressing potential energy. Okay, let's write that. That's a very useful way of expressing potential energy. Let's do the analogy here, right? So recall that, here you go. I'm going to use those two here. Those two equations come from those two equations. Recall that what? Recall that the electric force is going to be Q times E, right? Recall that the electric force is going to be something like that. Likewise, the electric potential energy is going to be the charge times the electric potential. One comes from the other, right? So likewise, here you go. We're going to need that, knowing that stuff here, knowing this relationship, now we can use the electric potential to solve problems, electric problems, in terms of conservation of energy. That's why you have to remember this relationship right in here. Going back here, potential difference. When a point charge moves from point A to B, it moves through a potential difference. Okay? So we can also here write it, potential energy difference and potential difference. That's what you have right in here. Okay, so go ahead and just, when an electric charge moves from one point having a given electric potential V1 to another one V2, we end up the charge, the electric potential energy of the charge ends up varying by the following amount. Here you go. When an electric charge Q, right? Q with a given electric potential V1, here you go. The electric potential energy of the charge ends up varying by the following amount. Here you go. Delta, delta, where 1 is the final minus initial. Final electric potential energy minus initial electric potential energy. Q times final potential minus initial potential, V2 minus V1. Okay. Okay, so let's talk about something else too. High potential and low potential, okay? If you have a charge distribution like that, the region of high potential, I'm not talking about high potential energy, the region of high potential is always there, that point in which you have a positive charge distribution. Okay, so whether it's a plate, whether it's a point charge, okay, so the whatever you have, the positive charge distribution is going to be the region of high potential, whereas in the negative region is going to be the low potential, no matter what. So keep that in mind. So here you go. If you have my battery, I know that the positive charges accumulate here in this tip. Just look at my battery here in the inset. Okay, so here is my region of high potential. Here is my region of low potential, because you have negative charge accumulated here and positive charge accumulated here. That's how we say. Okay, that's how we treat those. So if you have an electron beam and the electron beam is being attracted towards this charge, toward this plate here, I know that this plate is going to be positively charged. So in this specific case, the electric potential here below is going to have a high potential, whereas it's going to be at a high potential, at a higher potential, whereas this one is going to be at a lower potential, right? So we know that an electron beam is negatively charged, and if it's moving like that, it means that this plate is negatively charged, and this one is positively charged. So consequently, this one must be at a positive, at a higher potential, and this one must be at a lower potential. I already told you what is the potential due to a point charge. And just like the electric field, just like the electric force, we also have superposition of potentials, okay? So let's go to our example here that you saw. Multiple charge, right? That are interacting with one another. They have a potential energy between them. But in the region surrounding those three charges, we are going to have a net potential that's due, here you go, that's going to be due to the potential of the charge number 1, the potential of charge number 2, and the potential of charge number 3. Okay, so let's do here. That's one right in here, and this one. Okay, so the potential, electric potential right in here, I'm gonna write it down. The V the net V here is going to be V of 1 plus V of 2 plus V of 3. V of 2 and V of 3. Like that. At this point in space. That's what we call the superposition principle, just like we have for the electric field and the electric force. Okay? And then we can have a different electric potential somewhere else. Here you go. This one is going to be a V prime. V prime value given by V1 prime, V2 prime, and V3 prime. A different value. Here you go. One is point A, the other one is point B. Here you go. Let's call that point A. And the other one is point B. And how do we calculate that? Okay, let's calculate that. I'm doing for 3-point charges. I could have done for 2-point charges, right? If you have 2 or more point charges, okay, the electric potential at a given point in space is given by the superposition principle. Superposition principle. Here you go. It's going to be Q1. By the way, distance, and it's not gonna be any R. It's gonna be the distance to the charge 1, right? We're gonna have Q2, and again, it's gonna be distance to charge 2, and so on. If you have any charge, here you go. Oh. Which we go ahead and we represent by a summation. I'm gonna put it like here. Okay. And instead of small q, we're going to have BQ. And the distance here I'm going to represent by R sub I. And it's going to be from charge number 1 to charge number n, depending on the number of point charges. That's what we have here in the book. Here you go, potential due to 3-point charges. Where, right? You gotta tell me where. It's you cannot have a point right here at this charge. You cannot have it. You have to have a point. You cannot have a point right here at this charge, nor exactly at this charge, because you're not gonna have a finite number. You must have a point at different positions. Like he's asking for point A and point B. Let's do that. Here you go. Charge Q1, 4 microcoulombs. Charge Q2, 2 microcoulombs. Let's do that here in my software. Let's calculate the electric potential. Now we're going to talk about the electric potential, right? Q1, 4 times 10 to minus 6 coulombs. Q2, 2 times 10 to minus, oh, not here, 2 times 10 to minus 6 coulombs. Q3, lowercase q, Q3 minus 3 times 10 to minus 6 coulombs. We have their positions. 0, 0, you know, I'm gonna put here x1, x of 1 is 0, x of 2 is 3, and by the way, it's 3 centimeters with 3 to minus 2 meters, right? No, it's not x2, I meant y1, y1, and then we have x2, y2, right? x2, y2, x3, y3, oh, y3. What is x2? 10 to minus 2 meters. Oh, it should be y2, not y3. y2. Y2 is 0, right? Yeah, y2 is 0. x3. 2 times 10 to minus 2 meters. Oh, meters. And y3 is going to be what? 2 times 10 to minus 2 meters. Like that. Find the electric potential at point A. X equal to 0 and 1 equal to 0. Okay? Find potential at x equal to 0 and y equal to 0.01 meters. That's what he's asking. Charges, I'm going to put them all here. Here you go, this one. Right, how do we find out? Okay, we have 3 charges, we must have, okay, solution, right? Since we have 3 charges, then we're talking about the electric potential, not electric potential energy. Then we must have the sum of 3 potentials due to each charge. That's the difference between electric potential energy and electric potential, right? So what you're going to have at that spot, you're going to have V equal to V potential due to the first charge, potential equal due to the second charge, the potential due to the third charge. Okay? And each of those potentials are going to have a different equation. No, the equation is is similar, right? But the distance and the values are going to be different. Here you go. We're going to do R1, right? Next one is R2. And the next one is 3. Like that. Q1, 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 Q2, Q3 we already know. The question now is how to find out R1, R2, and R3. Okay. Okay, R1 is easy, right? All you gotta do is, here you go, it's gonna be this distance here. So how do we find this distance here? We find this distance in the following way. Here you go. R1, the generic way to write that down, it would be like equal square root of x1 minus x. Okay? What else? Just like the Pythagorean theorem, right? Plus y1 minus y. y1 minus y. And the same is applied to the other two. You go. R2, R3. R2 is this distance right in here. We're doing for A. And then we're going to do for B, right? Let's say potential point A due to the 3 charges. Okay, and then we're gonna do, B here. What was the charge? He has point B here. Well, we'll worry about that later on. Okay, so here you go. That's gonna be 2 and 2. That's gonna be 3 and 3. Right? That's how we find R1, R2, R3. Use the Pythagorean theorem. Let's see if it works. Let's say I know that Q1 to A is going to be 2 units. Okay? 0.02 centimeters. 2 centimeters or 0.02 meters. I know. Let's see if we get that. Here you go. If my I also have to write down the x, right? X is what? 0. And y is equal to what? Y is equal to 0.01 meters. Do like that. So here you go. I'm gonna substitute x1, y1, x, and y. Let's see if we get it right. It's supposed to be 0.02 meters, just like I got. 1, 2. R2. R2 is a little bit more difficult, right? But I can say that's gonna be square root of 2. Because it's this distance right here in the square there, 1 and 1. Let's see if you get it right. Y2 and x2, x and y, substitute for r. Oops. We got to calculate everything, expand, oops. And then we gotta expand again. Yeah, 0.014. Would be like 0.14 centimeters, just like I said before, square root of 2. X3 and Y3. Here you go. Go ahead and expand and take the square root. 0.022. This one is a little bit more difficult to find out. Okay, but it's gonna be this square plus this square root. And now we found R1, R2, R3. We can move ahead and calculate V1, V2, V3, right? We know as well that K is what? 9 times 10 to the 9 Newton. Newton what? Gotta remember that. Meter square over Coulomb square. Okay. Go ahead, substitute. Well, before I'm not gonna substitute R1 yet. I'm going to substitute V1, V2, V3 into my equation for V. So here, you got it. And now I can substitute everything, including my K. Oh, don't forget the Q as well. Q1, Q2, Q3. Did I put lowercase q? Gotta check if I did everything right. Yeah, I put lowercase 3. Here you go. We substitute everything. That's what I'm getting for the voltage, joules per coulomb, right? I'm gonna even put my K in a different unit. I'm gonna say that is joules meter per coulomb square. And when I do that, the software should refresh itself. Oh, by the way, this guy goes below my V3. That's what I'm getting for the volts. Joules per coulomb is volts. Let's see if that match what we have here in the book. Strategy, I did everything here. Blah, blah, blah. Hey. The potential at A is going to be, we know, 1.863 times 10 to the 6 volts. Just exactly what I got. What about item B? A point charge Q minus 5 nanocoulombs moves from a great distance to point A. Yeah, what's the change in electric potential energy? Let's do that. What's the change of electric potential energy of the system? Don't forget that item. And the charge is minus 5 nanocoulombs. Okay? So here goes. This is asking delta U of the charge of little q. Delta U of little q is going to be what? Is going to be the final potential energy that at point A minus the initial potential energy at a very large distance. That potential energy at a very large distance is going to be 0 at infinity distance. Okay, here you go. Right, yeah, right in here. But what else? The electric potential energy at A is going to be the charge Q times V at point A, which was exactly what I calculated here. Would have been better if I had put here V at point A. That would have been better. So I'm going to make it V at point A. I have the value. What about Q? We got to write down the value of Q, right? Q is going to be a negative 5 10 to minus 9 coulomb. Like that. 5 times 10 to minus 9. Here you go. We do that. And what I'm getting, we got a negative electric potential energy. Let's calculate everything. Here you go. I'm getting 0.0093266 negative joules. Let's see if we got it right. Okay, we did that. Yeah, times 10 to minus 3. Yeah, I got that times 10 to minus 3. Let's take a look here. Why did we get a negative? We got a negative for a very simple reason. The net charge of this distribution is positive, okay? And this negative charge is moving naturally from infinity to this distribution of electric charges, to that point A. Where the electric potential is positive. Okay, So conceptual problem. Okay, is the electric field zero at the center of the square? Is the potential, okay, you can do that yourself, right? Yeah, the electric field, let's see, is zero. Yes, positive away, all four charges. Yeah, the electric field is zero at the center of the square. Yeah, okay. But because the electric field is zero at the center of, remember, electric field is a vector, right? But just because the electric field is zero at the center of the square doesn't mean that the electric potential is going to be zero as well. Okay, in reality, the electric potential is not going to be zero. It's going to be a positive number. It's going to be the potential of this guy plus the potential of this one, the potential of this one, and the potential of this one. Let's see, they are all positive charges. The potential is not zero. Just because the electric field is zero doesn't mean that the potential is zero. Here you go. That's what's going to be the value of the electric potential at that spot. 4 times kq over r. Potential due to a spherical conductor. Okay? So let's do that. Well, let's take a break first, right? And I need to take a break, and I'll do that for you. Okay, next topic now is potential due to a spherical conductor. Okay, so we did something like that for the electric field. We remember that we're doing Gauss's law, and we calculated the electric field due to a spherical conductor. So that's what the notes are going to be about. Here we go. Potential, electric potential, right? Due to a spherical conductor. So recall that in the section for Gauss's law, we calculated the electric field for a spherical conductor. And do you recall what was the result? The result was the following, right? And we obtained the following. Here you go. Let's just take a look at that conductor again. Here you go. Let's see. Potential to a spherical conductor. Charged conducting sphere is the same out. A charged conducting sphere. Okay, and what we got is actually what he's talking about is the conducting sphere, a charged conducting sphere. That's what he's talking about. The electric potential due to a charged conducted spherical conductor, charged conducting sphere or charged spherical conductor. So what did you get there before? Right? We got that the electric field for a spherical conductor behaves, behaves just like a point charge. On the top of that, we also found that the electric field inside the conductor is zero. For the sake of this discussion, think about not as a spherical conductor, but a spherical shell, okay? A charged spherical shell. Uniformly. He didn't say that a spherical shell, but let's, due to a uniformly charged spherical shell. The book doesn't say that a spherical shell, but let's assume for the sake of this discussion that it is a spherical shell. So what do we get for the spherical shell? For the spherical shell, we got that the electric field outside the shell behaves just like that of a point charge. Remember that? And inside, because there was no charge inside, the electric field had to be 0. That's what we got there. And let's take a look at the graph for the electric field. Here you go. The graph for the electric field is just like that. See that? Point charge decreasing with the square of the distance, inside, outside, and inside, 0. So how do we find out the potential due to the spherical conductor? Well, okay, so that's the idea is to find out the potential due to a spherical conductor, okay? The idea is to determine the potential of a spherical conductor. How do we do that? How do we do that? Okay. So we do the following. If the field, if the spherical conductor, if the field of the spherical conductor, spherical shell, behaves just like a point charge, okay? So the potential must also behave like a point charge, okay? So we can say that outside the spherical shell, the potential can be written as here you go, of that of a point charge. Here you go, K Q over R. But just outside, okay? Electrical potential of the uniform charge spherical conductor, and I'm going to put more here, of radius R. Of radius R. That would be the, I'm going to even tell you that for little r greater than R. I can even put that equal as well. Sign is not just greater, but also is equal. The challenge now is to determine what is the potential inside the conductor. Okay. What's the potential inside the conductor? That's the challenge. Finding out the potential outside is just like that of the point charge. But what about inside the conductor? So that's the challenge. How do we find out the potential inside the conductor? Okay, mathematically, it's the following. Mathematically, it's the following. I didn't say that, and books don't say that, okay? But mathematically, there is a relationship between the electric field and the electrical potential, okay, folks? Here you go. It's something like that, delta V over delta R. Okay, like that. That's how the electric field relates to the electric potential. So if the field is 0, okay, so if, and by the way, that's not in the book, okay, if the field is 0, then, delta V must be 0 as well. Delta V must be 0 as well. If the field is 0 inside the conductor, then delta V must be 0 as well. That's one way of doing that. If delta V is 0 inside as well, What does it mean? It means that either the V is constant, either the V is zero everywhere inside the conductor, or it is constant, a non-zero value, a constant non-zero value. And what turns out to be is that the V inside the conductor is going to be a non-zero, or is going to be a constant of non-zero value. Okay? For this to happen, we have two possibilities. Either the V is zero inside the conductor, or V has the same value, has a non-zero uniform value inside the shell. Okay? What happens is the second one. Okay? What happens is the second one. That's one way of finding out. But the book shows you. Let's take a look in our book. The book explains in a rather different way. Okay? So here you go. Definitely this behaves the same way as a point charge. Okay? So here you go. We saw that field inside a charged conductor is the same as if all of the charge were concentrated in the point charge. As a result, the electric potential due to a conducting sphere is similar to the potential due to a point charge. We said that. Okay. So here is the graph, right, of the electric field, zero inside the conductor and outside the conductor. But what about the electric potential? Well, the electric potential ends up being a non-zero value, but ends up being uniform. And we have here a different way of explaining that. Okay? The electric field is zero. Because the electric field is zero, the force must be zero as well. And there must be no work that you can do inside the charge. So what does it mean? It means that the potential must be constant. And we choose a non-zero constant to make sure that the electric potential is continuous at this point here at the surface. That's how we can remember that. Okay? So at the surface of the conductor is going to be exactly KQ divided by big R, just like the book has spelled out. And inside also is going to be given by this value. Okay? Here you go. Since the electric field inside the cavity of material of the conductor is zero, no work would be done by the electric field or the electric force if you're to move around within the charge of the sphere. The electric field is zero, the force is going to be zero as well. Therefore, the potential anywhere inside the sphere is the same as the potential at the surface of the sphere. Okay, that's another way of explaining that. So let's take a look here at an example. This is an interesting example. Okay, you wish to charge a spherical shell. Now think about the Van der Graaf generator, as a spherical shell to a potential of very high of 240 kilovolts. On a day with average humidity and electric field of this value or greater, ionize their molecules, allowing charges to leak off the Van der Graaf find the minimum radius of the conducting sphere under these conditions. Okay? So the electric potential of the sphere is 240 kilowatts. And what do we want? We want to find out the radius of the conductor in which the electric field does not exceed this value here. That's what he's asking us to do. Let's go there to the notes. Going here to the notes. Example 17.6. Example 17.6. Okay? A spherical shell is charged to 240 kilovolts. Okay. Find if, here you go. If the electric field, I'm write that in a different way. If the electric field of this shell exceeds what? 8 times 10 to the 5th Newton per Coulomb. I'm going to copy that. That would be 800,000. Exceeds 800,000 newtons per Coulomb. The air around it is ionized, and the shell becomes discharged. Okay, becomes discharged. You wish to charge on an electric field allowing charge to leak. Find the minimum radius of this conductor under these conditions. Okay, so basically he's asking, find the minimum radius of the conductor in which you have this field value. That's what he's asking. 800,000 newtons per Coulomb, right? So how do we do that? Let's go to my software here. Okay, don't forget the electric field of your conductor is going to be KQ over R. You know that the electric potential at the surface, not divided by R, but R squared, right? R squared. The electric potential is KQ over R. And I want this guy to be less than that value that you saw. What must be the radius to get that? Okay. We want E to be less than 800,000 newtons per Coulomb. Okay. What must be R? That's what he's asking. What should be R for this condition? What must be R for this condition? Okay. Here you go. I'm going to do that. Volts. The minimum radius R for less than 800 newtons per Coulomb. Right? That's what he's asking you to do. Let's do that. Go. That's the condition we want. Let's do that. Here you go. We're going to to get this guy right in here. I know what K is. 9 times 10 to the 9, right? Joules meter per coulomb square. We can substitute in there. We know Q. You know K. We do not know Q. We do not know R. We do not know Q. Here you go. We don't know R, big R, and big Q. Two unknowns, and two equations. So in principle, we can solve that. V, we know that's 240K, right? Let's write that down here. I didn't put that. V is 240 times, let's do that. Here you go. V is 240 times 10 to the cube volts. Like that. I hate to have that the same unit for the but that's what it is. Two equations. I have the inequality for E. Here you go. The two equations are those two here. Those two right in here. Right? And that's the condition that you must apply. So let's I want to find out what is R, right? Oh wait, did it do that? No, I hate that. Let's see here what's going on. Okay. Let's try it again. Here you go. Yeah, I don't want that. Coulombs Q. R is square, right? Must be greater than this value. Let's solve for the square root. Yeah, that's the square root. I don't have Q. I do have K. Let's find out what Q is in terms of R, by the way, right? So what do? We substitute this value here. We solve for Q. We solve for Q, and we substitute for K. Here you go. Okay. I'm going to erase this guy for now. Okay. I will substitute my Q right in here. And let's substitute for K as well. Substitute for K. I didn't do that. Okay. Here's the volts, the unit volts. Okay. And we can solve now for R. Oh, I hate that. Why did he do that? Here you go. Okay, now I got it. The minimum radius is going to be this value here. Let's see. We gotta change the units, by the way. Let me erase this guy. Let me erase this guy. Let me erase this guy. Okay. Newton per coulomb is joules. Remember that? No, Newton per coulomb is it's not joules. This guy, let's see here. Well, of course, gotta be in meters, right? So Newton is what? Kilograms meter. Oops. Per second square. Per second square. Okay. And what about volts? Volts is what? Joules per coulomb. Okay, and joules is what? Joules is Newton times meter, right? Here we go. Let's continue here our calculation. Volts newtons kilogram meter per second square, and we must have a result in meters, 0.3 meters. Let's see if we got 0.3 meters. Okay, here we go. Yeah, 0.3 meters. That's the minimum radius of your Van de Graaff sphere at an electric potential of 240 kilovolts. So the electric field is not strong enough to ionize the air around and discharge the sphere. That's what it's all about. Do you remember what does it mean by ionizing the air, right? The book didn't explain that. Well, every time that you see that spark, it is you're iodizing the air. And when you ionize the air, all the charge of the sphere are being leaked towards the air around it. That's what's happening here. The book doesn't explain that, but that's what it means. Okay? So that's what we have for this chapter. You might want to look at potential difference in biological systems. You know, neurons have potential differences, the heart, muscle too. That's why we can use electrocardiograms. The brain also has electric potential difference that can be measured. That's why we have electroencephalograms and what they call electroretinographs. You can read that, and we can stop here right now. So see you again some other time. Bye-bye.